All right, so the last tail end of pH-metric titrations is pertaining the mathematical operations at the various stages of the pH meter curve. I'm going to do this in detail for strong acid, strong base, so something like HCl and NaOH, and you should know how to do each step. I'm going to briefly run through to show you, just for the sake of argument, the weak acid strong base, but you should for sure know this part, what we are covering in good detail. That doesn't mean you shouldn't know the other one, but I'm just saying this is more pertinent. But you should know what goes on in both of those. All right. Let's take a look at the various stages before you add sodium hydroxide, what happens at equivalence point, what happens after the equivalence point, what happens before the equivalence point, so in that flat region. So the four areas that we are going to take a look at: volume added, this is in general titrant, and it looks kind of like that. So we are going to take a look at the beginning. We are going to take a look at equivalence point, that should be pH 7. We are going to take a look in this region and in this region. So each of those, before any base has been added, before the equivalence point, at the equivalence point, and after the equivalence point. Now, we are starting with a scenario that we have a strong acid, something like HCl, and we have 50 milliliters of that in a flask. So I have 50 milliliters of 0.02 molar HCl in a flask. And to that, I'm going to be adding sodium hydroxide. And I know that the concentration of sodium hydroxide that I have is 0.03 molar. So before any sodium hydroxide has been added, first things first, you should calculate the overall total number of moles that are present, the moles of HCl that are present. So before you add any base, what concentration you have, how many moles you're beginning with, let's take a look at that each step. So since you know that HCl is a strong acid, that means that HCl is going to completely dissociate to give you H plus and Cl minus. That means whatever is the concentration of HCl, same as the concentration of H plus or hydronium, however you want to call it. And that means that you can straight away take a negative log of this 0.02 to get the pH. And when I did that on my calculator, I'm getting a value of 1.70. That means my pH curve is supposed to start. So if this is 1, this is 2, this is 1.5, it's in between. This is the point where it's going to begin, right? And then it's going to increase, and then a huge point of inflection and work like that. Now, of course, how it's going to inflect and what kind of volumes we are looking at, it's going to depend on the rest of the parameters that have been provided. But we do need to begin at a pH of 1.70, and as we add sodium hydroxide at any step before the midpoint, so all of the, maybe these regions, this is the point of time where the equivalence point has not been reached, and that would mean that the pH would continue to rise unless it's ready to hit the point of inflection. Now, and again, like I said, you can select any value, any amount of volume that has been added. So I'm going to actually show you the math step by step. So we'll do some chalk talk here. So my graph, like I said, this is 1, this is 2, this is 1.5. So in between is what I have, and subsequent additions are going to be slightly higher than the 1.7, so they're increasing until unless it hits the point of inflection. Now, just to get a feel for how much volume will be required to achieve equivalence point, I'm going to calculate the moles of HCl that I have in my flask. So since I have been given 0.020 molar solution, and I have 50 milliliters of that, of course you will need to convert the milliliters into liters, so that's why I used 0.05, and molarity, you know from chapter 11, is moles per liter. When you work out the math for that, that's going to be 1 times 10 to the power of -3 moles. That's what you would end up getting for HCl. And you have the molarity for sodium hydroxide. The question is, what volume of sodium hydroxide do you need so that you have achieved your equivalence point? Now you know that at equivalence point, moles of HCl are going to be equal to moles of NaOH. So what that means is 1 times 10 to the power of -3 divided by 0.03 moles per liter is going to give you your volume, since molarity times volume, moles per liter times liter. So from here you would be able to get liter going as the numerator. You would be able to determine your volume in liters, and that comes out to be 0.0333, or you can say 33.3 milliliters. So if you have added 10 or 20 or 30, and let's say this is 40, so in around here is when the point of inflection should be or would be. So that means any volume before the 33.3 milliliters, that would be subject to one of your data points, and then of course any volume greater than that. And so you can pick any number like 40, 45, 55, whatever you want to, and you can pick any number less than 33.3 to measure this region. So these are the two regions that we are going to take a look at. So that's why it's important to kind of get a feel for what volume of the titrant you would need for that reaction to take place. Now, as you add the sodium hydroxide into the solution, it's going to neutralize the hydronium. So the reaction that's occurring in this region right here is that the added OH negative is interacting with the hydronium ion, and it's giving you 2 molecules of water. And because this is a strong acid, strong base titration, this reaction is going to be driven all the way to neutralization towards the product side. So you can calculate the amount of hydronium ion at any given point of time before the equivalence point by simply using the stoichiometric relationship that 1 mole of the hydroxide is going to neutralize 1 mole of the hydronium. Now, my initial moles in the system are 1 times 10 to the power of -3 moles. That's what I am beginning with. If you pick some volume of base added, let's say you have added 15 milliliters, okay? So for 15 milliliter of the base added, I want to calculate moles of base. Since you had 0.03 molar sodium hydroxide moles per liter NaOH, and you have added 0.015 liters of sodium hydroxide. So the liter and liters will cancel off, and you're going to end up with, let me just plug that number in. I am punching in on my calculator 0.03 times 0.015. So that gives me 0.00045, or you could say 4.5 times 10 to the negative fourth moles. And it kind of makes sense based on what you have added. The moles of acid, because you're before the equivalence point, the moles of acid here, moles of acid should be more than moles of base. So it makes sense of, for the numbers that we have. Now, let's take a look as to, let's take a quick look as to what it would look like in terms of the number of moles of hydronium ion which will be left over. So since we have the acid, which is 1 times 10 to the third, we have the base, which is 4.5 times 10 to the negative fourth, we can say that moles of hydronium left over is going to be 1 times 10 to the power of minus 3. From that, I'm going to subtract 4.5 times 10 to the negative 4, because you know that for each mole of sodium hydroxide, the same number of moles of HCl is going to get neutralized. So this amount is going to get neutralized. So that's why we are subtracting. And when you do that, so I'm plugging that value in, 0.001, from that subtracting, so I'm 0.00045, 55 is what should remain, yep. So my answer comes out to be 5.5 times 10 to the negative fourth. These many moles of hydronium of HCl remain. Well, they remain, but realize that you have added a little bit of acid into the system. So you should divide these number of moles by the total volume that you have in there. And so you originally started with 50 milliliters and you have added 15. That means your total volume is 0.065 in liters. And so you divide that number by 0.065, which is the volume, and that gives you the molarity of HCl, which is 8.46 times 10 to the negative 3. And if you take this number and you simply take the log of that, you're going to take negative log of 8.46 times 10 to the negative 3. You're going to end up with 2.07. 2.07. It still is an acidic pH, but you have crossed over, and that makes sense that as you have added sodium hydroxide, the pH is slowly rising. So again, the steps to figure out the pH right before equivalence point is A, you must first calculate what volume of the base would you need for this process to occur, and we determined for our case that happened to be 33.3 milliliters. What that means is any volume less than 33.3 is going to drive the pH and keep it still in the acidic region because the neutralization is going to take place between the added sodium hydroxide and the HCl that you have in the system. So at this point of time, it really is up to you which volume you want to go with. So I just randomly picked like number 15. You can do 10, 20. I think in the slide I picked 20, but you can pick whichever you want to as long as that value is less than 33.3, because realize that at 33.3 the equivalence would have been achieved. So of course, if you continue to add, let's say you put in 20 or 30 milliliters, the pH is going to continue to rise. So those are these, those are, let's maybe use a black color. So if that's, you're going to see for the case of 20, you're going to see for the case of 30, you saw for, it's going to slowly rise. So that's the path that it has taken. Now, at equivalence point, the pH at equivalence point for a strong acid, strong base must always be 7, because at that point of time, you're going to see, so 3, 4, 5, 6, and 7. Again, this is not to the scale. Realize that the pH is 7, and we say that it is 7 because it's a neutral salt that you get at equivalence point. The strong base has completely neutralized the strong acid. The only source of hydronium ion then is going to be the ionization of water, and since the ionization, you already know from chapter 15, is 1 times 10 to the negative 7, when you take the negative log of that, the pH is going to come out to be 7.00. So realize that a pH is already preset to be 7. And if you now continue to add the sodium hydroxide, since you have already neutralized, the titration is pretty much complete, and now whatever is the excessive hydroxide that you see, that's going to essentially increase the pH and bring it in the alkaline region. So that's what we are going to take a look at. So this is what I say here as well, that at equivalence point, pH is 7, and we already determined that this value was 33.3 milliliters, and we showed that, and the pH is going to be set at 7. So that was pretty straightforward. After the equivalence point, so once we have been through the equivalence point, and now we are adding excessive hydroxide, so beyond the equivalence point, essentially the sodium hydroxide becomes the excess reagent. So what we are going to do is we are going to calculate the number of moles. Again, we are going to take a look at the total volume, and much the same way as we did before the equivalence point, we are going to take a look after the equivalence point and go with that. So since we did, 33.3 milliliters was our equivalence point, and again here I'm doing 45, but I'm going to show you the math separately so you follow every step with me. I'm going to pick, some number, let's say it's 40, so we have some points to plot in my data curve as well. Let's see again. This is my pH, this is my volume, 10, 20, 30, 40, 35 is here, so 33 is probably here. This is where my equivalence point is supposed to be. Let's say that's 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And I started with 1 point some, and upon addition of 15, I got a 2.07, so approximately it was here. So this is what it kind of looks like, and then it will achieve pH 7, so it will become like that, and then it'll go like this. So we are done with points A, B, and C. Let's say I need to determine at point D. So I have added, if this is 40, 50, suppose this is 60. This is the part, okay? So I have added 60 milliliters. 60 milliliters, my base concentration was 0.3 molar. So I want to determine the moles of hydroxide that I have in my system. So I have deposited 0.03 moles per liter times 0.06 liters. So that comes out to be, upon multiplication, that comes out to be 0.03 times 0.06. That's 1.8 times 10 to the negative 3 moles. Now realize this is the total that you have deposited, and of course some of it was utilized in neutralizing the HCl. Now the moles of HCl that you began with, that you had in your system in the first place, was 1.3 1 times 10 to the negative 3 moles of HCl, and all of those have been exhausted. So essentially you can say that HCl became your limiting reagent. And so in such a scenario you would say, what is remaining? Remaining OH negative. Now you would say the difference between the two, 1.8 times 10 to the negative 3 minus 1 times 10 to the negative 3, so 8 times 10 to the negative 4 of the hydroxide is present. But how much volume is it present in? You already had 50 milliliters of HCl, and you have added 60 milliliters of sodium hydroxide. So that number divided by 110 milliliters is going to give you your hydroxide concentration. So if I were you, I would convert the milliliters into liters, and before you carry out that division, and so I have 8 times 8 times 10 to the negative 4th, and I'm going to divide that by 0.11, and that will give me 7.27 times 10 to the negative 3. And if you take a log of that, you would basically be determining the pOH in this case, which comes out to be 2.13. And if pOH is 2.13, pH should be 14 minus 2.13, which gives you 11.86. And that is your overall pH. So again, realize before you added any base, you started with an acidic pH. Before the equivalence point has been achieved, you are going to maintain that acidic pH because you're still adding that. Equivalence point has not been achieved. At equivalence point, neither reactant is in excess, so pH is going to be 7. And beyond the equivalence point, which is this region for point D, OH negative is the one in excess. So you are going to calculate the concentration by subtracting the initial number of moles of hydronium from the number of moles of the added hydroxide, and then divided by the total volume. So just to make sure everybody's on board, at B, hydronium is in excess. This is excess. At D, hydroxide is in excess. At C, hydronium is going to be equal to hydroxide. That is why the pH is 7. Okay, I hope that made sense. There is actually a practice problem in your Dry Lab 3 that you can work on. I'm going to just work on a couple more problems just to make sure everybody's on board, and give you just the basics for the titration of the weak acid and strong base, how to go about that, and that will be it for this part of the chapter.